Right now, 26,000 light-years away, something is happening at the center of our galaxy, and scientists have no idea what it is. A black hole 4 million times heavier than our Sun sits there. Objects circle it that survive forces that should destroy them. An invisible wall blocks the fastest particles in the universe. A massive ball of mysterious light glows with no confirmed source, and random radio signals switch on and off with no pattern. If you enjoy space mysteries that actually keep researchers up at night, hit like and subscribe. It helps a lot. Every answer we find out there raises 3 new questions, and the strangest ones are dead ahead. Prepare yourselves. We begin. The year was 1951. A young astronomer named Karl Jansky was supposed to be tracking down the source of interference messing with transatlantic phone calls. He expected to find thunderstorms. He expected boring results. What he found instead would change science forever. Jansky built a rotating antenna in a field in New Jersey. It looked like a merry-go-round made of pipes and wooden beams. He spun it slowly, pointing it at different parts of the sky, listening for crackling static. Most of the noise matched up with storms on the horizon, but one signal refused to behave. It came back every single day. It shifted slightly with each sunrise. And after months of tracking it, Jansky realized the signal was not coming from Earth at all. It was coming from the center of the Milky Way. He published his findings in 1933. The scientific world barely blinked. Astronomers at the time were focused on visible light. The idea that the sky was broadcasting invisible radio waves felt too strange to take seriously. Jansky moved on. The discovery sat mostly ignored for over a decade. Then a plumber turned amateur scientist named Grote Reber built a dish antenna in his backyard in Illinois and picked up the signal himself. He mapped it carefully. The strongest point on the entire map was a single location, dead center of the galaxy, a spot in the constellation Sagittarius that blazed brighter in radio waves than anything else in the sky. Scientists named it Sagittarius A, not a star, not a nebula, something else entirely. Here is what made that discovery so unsettling. Radio waves from space come from extreme events: exploding stars, colliding gas clouds, superheated plasma spinning at incredible speeds. Whatever was sitting at the center of the Milky Way was producing enormous amounts of energy. But when astronomers pointed their best optical telescopes at that exact location, they saw almost nothing. A thick wall of dust and gas between Earth and the galactic center swallowed visible light completely. The core was screaming in radio waves and completely invisible to the human eye at the same time. Scientists knew something massive was there. They just could not see it. For the next few decades, radio astronomy became a race to figure out what that central source actually was. Better equipment revealed that Sagittarius A was producing energy across multiple wavelengths: X-rays, infrared light, radio bursts of varying intensity. Whatever sat at the center was active. It was feeding on something. And the sheer volume of energy pouring out of that single point suggested a scale that was hard to process. Think of it this way. The sun releases energy equal to about 400 trillion watts every second. The central source of our galaxy was outshining that by factors that made the sun look like a candle next to a stadium floodlight. By the 1970s, a leading theory emerged: a supermassive black hole, an object so dense that nothing, not even light, could escape its gravity. Scientists suspected one sat at the center of nearly every large galaxy. The question was whether ours had one too. The signal Jansky heard from that New Jersey field pointed straight at it. What came next was a decades-long detective story, and the clues were moving. Pull back far enough from Earth, and the Milky Way looks like a flat spinning disk with a bright bulge at its center. That bulge is the galactic core, and for most of human history, we had no idea where inside that disk our solar system actually sat. In the early 20th century, the astronomer Harlow Shapley made the first serious attempt to figure it out. He studied clusters of old stars scattered around the galaxy and noticed they were not spread evenly. They clumped in one direction of the sky much more than others. He used that lopsided pattern to triangulate the center. His estimate was rough, but the direction was right. The center of the Milky Way sat somewhere toward the constellation Sagittarius. The official distance measurement came in 1985. Scientists used the best data available and landed on a number of about 27,700 light-years from Earth to the core. That number became the standard. It got printed in textbooks. It got used in calculations. For 35 years, it was accepted as settled. Then, in 2020, a team running one of the most detailed maps of the galaxy ever attempted revised that number. The real distance, using dramatically improved precision instruments, turned out to be about 25,800 light-years. The Sun was 2,000 light-years closer to the galactic center than anyone had officially measured. 2,000 light-years sounds abstract, so here is a way to feel it. Light travels about 6 trillion miles in a single year. 2,000 light-years is 12 million trillion miles. We were off by that amount. That is how hard it is to measure the inside of the galaxy while you are also inside it. Standing on Earth and trying to map the Milky Way is like standing in the middle of a crowded concert trying to sketch a blueprint of the entire stadium. Dust blocks your view. Stars overlap each other. Everything is moving at once. That 1985 measurement was off for a reason. The same thick dust and gas that hides the galactic core in visible light also messes with distance calculations based on optical observation. The 2020 team used radio wave and infrared tracking to cut through the dust and get cleaner data. The result shifted our understanding of where we live inside our own galaxy. Here is why that matters beyond just updating a number in a textbook. The position of the Sun inside the Milky Way affects how our solar system moves through space. The galaxy rotates. Everything in it orbits the center at different speeds, depending on how far out it sits. A more accurate position gives scientists a more accurate picture of the Sun's true speed and path through the galaxy. That number affects predictions about where we have been, where we are heading, and what we might pass through over the next millions of years. And here is the part that should give you pause. If we were off by 2,000 light-years on something as basic as our own address in the galaxy, what else in our cosmic map is slightly wrong? The galactic center sits 25,800 light-years away, close enough that the energy and events happening there can be studied in detail, far enough that we are safe from almost everything it does. Almost, because the things happening at that center are stranger than any distance makes comfortable, and one of the strangest things of all is what actually lives there. For a long time, the idea of a black hole at the center of our galaxy was a theory, a strong one, a well-supported one, but still a theory. Proving it required something nearly impossible. You had to find evidence of an object you could not see, in a location you could barely observe, using instruments that were only just powerful enough to try. The proof came slowly, over decades. The first strong clue arrived in the 1980s, when astronomers started tracking individual stars near the galactic center using infrared telescopes. Infrared light cuts through the dust clouds that make the center invisible in regular light. For the first time, scientists could actually watch stars that lived near the core, and what those stars were doing made no sense unless something enormous was pulling them. The stars near the center were moving fast, extremely fast. Stars farther out in the galaxy drift along at relatively gentle speeds compared to what was happening in that central region. These inner stars were racing, curving, looping in tight orbits, the kind of motion that only happens when a massive gravitational anchor is pulling everything toward a single point. Think of it like swinging a ball on a string. The shorter the string, the faster the ball has to travel to keep from flying off. The stars nearest the galactic center were on very short strings. That meant something with enormous mass was at the end. Two separate teams spent over a decade tracking the same group of stars. One team was based in Germany, the other operated out of the United States. They used different telescopes on different continents, checked each other's work without coordinating, and arrived at nearly identical conclusions. The mass pulling those stars into their tight orbits was equal to about 4 million times the mass of our Sunday, and it all fit inside a region smaller than our solar system. There is only one thing in physics that can pack 4 million solar masses into that smaller space: a supermassive black hole. The German team calculated the mass at 4.15 million solar masses. The American team came in at 4.3 million. Both numbers confirmed the same object. That convergence from two independent groups using completely different data is one of the strongest forms of scientific confirmation that exists. The two lead scientists, Andrea Ghez and Reinhard Genzel, shared the Nobel Prize in Physics in 2020 for this work. But here is what is worth sitting with for a moment. A black hole does not emit light. You cannot photograph it. You cannot point a telescope at it and see it the way you see a star or a planet. What Ghez and Genzel proved was its existence through absence. Through the behavior of everything around it, the black hole itself remained hidden. Only its grip on the nearby stars gave it away. It is like finding a whirlpool in the ocean and concluding there must be a drain at the center, even though you cannot see the drain. The object is confirmed. Its mass is confirmed. Its location is confirmed. What surrounds it is where things stop making sense. Because the stars orbiting that black hole are doing something that nobody predicted. Once astronomers confirmed a supermassive black hole at the galactic center, the next question was obvious. What is actually orbiting it? The answer turned out to be a collection of stars moving in ways that challenged everything the models expected. The black hole sits surrounded by a dense cluster of stars called the S-cluster. These are young, massive, hot stars, the kind that normally form in calm regions of a galaxy where gas clouds can slowly collapse and build new suns over millions of years. The galactic center is the opposite of calm. The gravity near a 4-to-million solar mass black hole is violent. Radiation blasts through the region constantly. Gas gets heated and torn apart before it can settle into anything stable. Young stars forming there should be nearly impossible, and yet there they are. Astronomers call this the paradox of youth. These stars exist in a place where their existence is hard to explain. One leading theory is that they formed farther out in the galaxy, inside a dense cluster of stars that migrated inward over time. Gravity from the black hole slowly drew that cluster in. The cluster eventually broke apart, and the individual stars scattered into the orbits we see today. That theory fits the data reasonably well, but it has never been fully confirmed. The star tracked most closely is called S2. Its orbit takes about 16 years, making it one of the fastest orbiting stars ever recorded. At its closest approach to the black hole, S2 travels at nearly 3% of the speed of light. That is roughly 20 million miles per hour. A fighter jet flying at full speed would take about 300,000 years to match even 1 second of S2's peak velocity. At that speed, Einstein's theory of general relativity becomes measurable in real time. When S2 swings close to the black hole, its light shifts slightly toward the red end of the spectrum. Gravity is so strong at that distance that it literally stretches the light waves coming from the star. Scientists detected this shift with high precision during S2's closest pass in 2018. The measurement matched Einstein's predictions almost exactly. That was a direct test of general relativity in one of the most extreme gravitational environments in the known galaxy. And it passed. But other stars in the cluster behaved less cleanly. Some showed small deviations in their orbits, tiny wobbles that the standard black hole model could not fully account for. Scientists proposed several explanations: hidden smaller black holes orbiting alongside the big one, dense clouds of dark matter clustering near the core, or simply measurement error from the extreme difficulty of tracking objects 26,000 light-years away. None of those explanations has been ruled out. And then there are the 6 objects sitting even closer to the black hole than any of these stars. Objects that move like stars but look like gas. Objects that by every law of physics should have been destroyed years ago, they survived. And nobody fully understands how. For decades, the black hole at the center of our galaxy was proved through math and motion. Scientists knew it was there. They had measured its mass. They had tracked the stars orbiting it, but they had never actually seen it. Then on May 12th, 2022, that changed. A global network of radio telescopes called the Event Horizon Telescope released an image. It showed a glowing ring of orange and gold light surrounding a dark circular shadow. That shadow was the event horizon of Sagittarius A star, the actual boundary of the black hole, the point beyond which nothing returns. To capture that image, scientists linked 8 radio telescope observatories scattered across the globe into one enormous virtual telescope. Dishes in Hawaii, in Chile, in Spain, in Antarctica, and several other locations, all aimed at the same point in the sky at the same time. Together, that network had the resolving power of a telescope the size of Earth. Even so, capturing an image of the galactic center black hole was staggeringly difficult. The reason the image took so long to release after the data was collected comes down to one specific problem. Sagittarius A star is messy. The material swirling around it moves fast, very fast. Gas and plasma orbiting the black hole completes a full loop in just a few minutes. The black hole at the center of the galaxy, Messier 87, which the Event Horizon Telescope had already photographed in 2019, was so large that material took days to orbit. That slower pace made it easier to capture a stable image. The galactic center black hole changes so rapidly that stitching together data from multiple telescopes over multiple observation windows was like trying to photograph a spinning top with a camera that takes several hours per shot. Scientists had to develop entirely new algorithms to average the motion and extract a clear image from the noise. The result confirmed the mass estimates almost perfectly. The shadow was exactly the size predicted by general relativity for an object of 4 million solar masses. The match between prediction and observation was striking. But the image also raised a question nobody had cleanly answered before. The glowing ring surrounding the shadow is hot gas. It is material falling into the black hole, heated to extreme temperatures as it spirals inward. That gas should be producing enormous amounts of radiation on a constant basis. Yet astronomers have measured surprisingly quiet periods at the galactic center, days when the black hole barely flickers. Then, sudden massive flares where its brightness jumps by a factor of 75 in under an hour. Those flares have no confirmed trigger. Scientists have proposed that clumps of gas fall in suddenly, producing bursts of energy. Others suggest magnetic field reconnection events. The same process that causes solar flares on our sun briefly supercharged the material near the event horizon. Both remain theories. The image gave us a face to put to the mystery, but the behavior behind that face is still deeply strange. What the image could not show was everything happening just outside the event horizon, the objects circling just beyond, the invisible forces at work, the things that survive when nothing should. Science is supposed to produce fixed answers. You measure something carefully enough, and the number settles. But the galactic center keeps refusing to cooperate. The distance to the core has shifted multiple times as technology improved, and each revision has carried real consequences for how we understand our place in the galaxy. The problem starts with location. Earth sits inside the Milky Way, roughly 2/3 of the way from the center to the outer edge. Measuring the distance to the core from inside the galaxy is genuinely hard. You cannot step outside and look back. You have to use the stars around you as reference points, measure their distances, track their motions, and build a map from scratch while everything, including you, is moving. The first serious estimate, made by Harlow Shapley in the early 20th century, placed the core at roughly 50,000 light-years. That number was way off, but it was a start. Better instruments through the mid-20th century brought the estimate down. By 1985, the International Astronomical Union, the official body that sets standards in astronomy, locked in a value of 27,000 700 light-years. That number went into textbooks and stayed there for over 3 decades. In 2020, the Vera collaboration, a Japanese radio astronomy project using a network of telescopes spread across the country, produced the most precise map of the galaxy ever created at that time. Their measurement, 25,800 light-years, a difference of nearly 2,000 light-years from the official figure. That is a significant revision. And it came with a second surprise. The same dataset showed the Sun is moving around the galactic center faster than previously measured. The older speed estimate was about 136,000 miles per hour. The new measurement put it closer to 150,000 miles per hour. We are moving faster through the galaxy than the textbook said. Both the new distance and the new speed affect every calculation that depends on our position. Estimates of how long it takes the Sun to complete one full orbit of the galaxy. Predictions of what regions of space the solar system will pass through in the distant future. Models of how different parts of the galaxy interact with each other. All of those get adjusted slightly when the baseline numbers shift. Here is the part worth sitting with. The Vera project used a technique called parallax, tracking the tiny apparent shift in a star's position as Earth moves from one side of its orbit to the other. That technique is extremely reliable at shorter distances, but gets harder the farther out you go. At galactic scales, even the most precise instruments carry a margin of uncertainty. The 2020 number is the best we have. It is almost certainly closer to true than the 1985 number, but it may not be the final answer either. The galactic center sits close enough to study in detail, but far enough that every measurement is still an approximation. And if our most basic measurements of distance and speed keep shifting, then every conclusion built on top of those measurements carries at least a small asterisk. That asterisk gets bigger the closer you look at what is actually happening at the center, because some of what is happening there breaks the models even when the measurements are exact. In 2004, a team of astronomers tracking stars near the galactic center noticed something that did not fit. Among the bright, fast-moving stars orbiting Sagittarius A star, there was an object that behaved differently. It moved like a star, but it looked like a cloud of gas. It was fuzzy at the edges, stretched out, warm in a way that gas clouds near a black hole should not stay for long. They catalogued it and moved on. Then they found another one, and another. Today, 6 of these objects are confirmed in the same region. Scientists call them G objects, with the first 2 discovered named G1 and G2. Their orbital periods range from 170 years for the shortest to 1600 years for the longest. They orbit in a cluster around the black hole, tracing paths that take them uncomfortably close to the event horizon before swinging back out. Here is what makes them strange. The region immediately surrounding Sagittarius A star is one of the most hostile environments in the galaxy. Gravity near the black hole is powerful enough to pull a gas cloud apart through a process called tidal disruption. Imagine taking a water balloon and stretching it from both ends until it snaps into droplets. That is what should happen to a cloud of gas that passes too close to a 4-to-million solar mass black hole. The G objects pass that close. They should be droplets, but they come out the other side intact. The discovery that forced everyone to take this seriously happened in 2014. G2, the second of these objects discovered, was heading toward the closest point in its orbit around the black hole. Astronomers around the world pointed telescopes at the galactic center and waited. The models predicted G2 would be stretched apart. Its gas would fall into the black hole and produce a massive flare of energy, a light show visible across the galaxy. Scientists set up observation campaigns specifically to watch the destruction. G2 reached its closest point. The black hole stretched it. The object elongated, smearing out along its orbital path into something that looked like a comet tail. And then it snapped back. G2 reformed. It pulled itself back together and continued its orbit, slightly changed, but fundamentally intact. The fireworks never came. That result sent astronomers back to their models. A pure gas cloud cannot do that. Gas, once stretched by extreme gravity, does not reassemble. Something inside G2 was providing structural stability, something solid. The leading theory today is that G objects are binary stars, pairs of stars orbiting each other closely, that merged into a single object at some point in the past. When two stars combine, they produce a bloated, expanded stellar body surrounded by a thick shell of gas and dust. That dusty outer layer makes them look like a gas cloud from the outside, but the merged stellar core inside holds the whole thing together when gravity tries to rip it apart. This theory is plausible, but astronomers cannot see inside the G objects. The dust blocks the view. The merged core, if it exists, remains unconfirmed. 6 objects surviving where survival seems impossible, and the mystery surrounding them only gets stranger when you learn what else orbits the black hole nearby. The year 2014 gave astronomers something genuinely rare, a front-row seat to what might be a cosmic catastrophe. Scientists had been tracking G2 for 2 years by that point. They had measured its trajectory, calculated its closest approach, and run the numbers. Everything pointed to a dramatic end for the object. Stefan Gillissen, an astronomer at the Max Planck Institute in Germany, was part of the team that first spotted G2 in 2011. When he realized what the orbit implied, he described the upcoming event as the most interesting thing happening in the galactic center in his career. Observatories around the world started scheduling telescope time. Papers were published predicting the outcome before it even happened. The models were specific. G2 would pass within about 130 astronomical units of the black hole. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So G2 was predicted to swing within 12 billion miles of a 40 million solar mass black hole. At that distance, tidal forces become overwhelming. As G2 approached, telescopes tracked it in infrared light. The object began to stretch. That part matched the predictions perfectly. By early 2014, G2 had elongated visibly, its leading edge being pulled faster than its trailing edge by the black hole's gravity. Astronomers watching the live data saw exactly what they expected to see. Then the leading edge swung around the black hole and started heading back out, and G2 followed it. Over the following months, the elongated shape began to contract. The tail caught up with the head. By late 2014 and into 2015, the object had pulled itself back together. The bright flare of infalling material never came. The dramatic increase in radio and X-ray emission that would signal a feeding event never arrived. Sagittarius A, star, barely blinked. G2 had survived. The scientific community processed this result in stages. First came the attempts to explain it away. Maybe the object had already partially disrupted, and the main debris had simply not reached the black hole yet. Maybe the expected flare was delayed. Astronomers watched for several more years. The flare never came. Then came the harder admission. The models were wrong. G2 contained something the pure gas cloud model could not account for. This was significant beyond just one object. The G2 event was supposed to be a chance to observe a gas cloud feeding a supermassive black hole up close. Those events, called tidal disruption events, happen regularly across the universe. They produce enormous bursts of light. They help scientists understand how black holes grow. G2 was supposed to be the closest and most detailed example ever observed. Instead of answering questions, the G2 survival opened new ones. How many other objects near the galactic center are also secretly solid inside their cloudy shells? What do these merged stellar remnants tell us about the history of star formation in that region? And what does the black hole's failure to consume G2 say about how it actually feeds? The survival of G2 sits in the data now, confirmed and unexplained in equal measure. The next chapter goes even deeper into what these objects might actually be, and the answer involves 2 stars dying together. The survival of G2 forced astronomers to come up with a new explanation. a pure gas cloud falls apart under extreme gravity. Something inside G2 held it together. The most widely accepted theory today involves binary stars, and it is both elegant and deeply strange. A binary star system is two stars orbiting each other. These are common. Roughly half of all stars in the Milky Way are thought to travel in pairs. In calm regions of the galaxy, binary systems can orbit each other for billions of years without merging. But the galactic center is not a calm place. The gravity of Sagittarius A star exerts an enormous tidal influence on everything nearby. When a binary star system drifts too close, the difference in gravitational pull between the near side and the far side of the pair becomes strong enough to push the two stars toward each other. Over time, their orbit tightens. They spiral inward. Eventually, they collide and merge. This kind of merger produces something unusual. When two stars combine, the resulting object is much larger and bloated than either original star. The collision kicks out gas in all directions, wrapping the merged body in a thick, warm envelope of stellar material. From the outside, this combined object looks like a gas cloud. It is fuzzy. It glows at the right temperatures to register as gas. Infrared telescopes see exactly the kind of emission you would expect from warm gas rather than a solid star. But inside that cloud, the merged stellar core is still there, dense enough and massive enough to resist being torn apart by even the black hole's gravity. Think of it like a hard-boiled egg wrapped in cotton. The cotton looks soft and falls apart if you pull it, but the egg inside stays whole. The G objects, under this theory, are galactic center binary stars that merged sometime in the past few thousand years, still wrapped in the leftover material from their violent union. As they continue orbiting the black hole, they will slowly shed that outer gas shell. Over tens of thousands of years, the merged core will be exposed. At that point, it will look like an ordinary star in an extraordinary orbit. Andrea Ghez and her team at UCLA published work supporting this merged binary model after the G2 event. The math worked. The expected size, temperature, and behavior of a recently merged binary system matched what telescopes observed in the G objects. But this is still a theory, confirmed in the sense that it fits the data, unconfirmed in the sense that no telescope has directly imaged the stellar core hiding inside any G object. The dust is too thick. The objects are too far away. The galactic center is too cluttered with competing sources of light and heat to isolate what lies at the center of G2 or its 5 siblings. 6 objects, 6 possible merged binary remnants, all orbiting a 4 to million solar mass black hole in a region packed with fast-moving stars, extreme radiation, and gravitational forces that should not allow any of them to exist. And that is just the stars. Something even stranger wraps around the entire galactic center from the outside, invisible and completely blocking the rest of the galaxy from getting in. The galactic center has a door, and it only opens one way. Scientists confirmed this in 2020 when data from the Fermi Large Area Telescope revealed something nobody had predicted. The central molecular zone, the massive region of gas and dust surrounding the galactic core, is almost completely empty of cosmic rays coming from outside. Cosmic rays stream through the rest of the galaxy constantly, traveling in every direction. They pass through open space, through star clusters, through nebulae. Almost nothing stops them, but at the edge of the central molecular zone, something does. Cosmic rays from the wider galaxy hit a boundary and stop. The density inside the zone drops sharply compared to what the standard models predicted should be there. Something at the edge of the central region blocks incoming particles while still allowing the particles produced inside to escape outward, an invisible wall. Confirmed by the data, mechanism completely unknown. To understand why this is alarming, it helps to understand what cosmic rays actually are. They are not light. They are actual particles, protons and atomic nuclei, traveling at speeds approaching the speed of light. A single high-energy cosmic ray carries more kinetic energy than a baseball thrown by a professional pitcher, packed into a single subatomic particle. They are produced by exploding stars, colliding galaxies, and the violent regions around black holes. They travel freely through the universe, rarely interacting with anything because space is mostly empty. So finding something that stops them cold is remarkable. The boundary appears to sit along the edge of the central molecular zone. Inside that zone are roughly 60 million solar masses of dense gas. That is enough raw material to build 60 million stars the size of our sun, all compressed into a region spanning about 900 light-years across. This cloud of gas is the fuel supply sitting next to the galactic engine, and the cosmic ray barrier wraps around it like a one-way membrane. What actually causes it? Two main theories compete. The first involves magnetic fields. The galactic center generates powerful magnetic fields, far stronger than the average field found throughout the rest of the Milky Way. Some researchers propose that these fields compress at the boundary of the central molecular zone, creating a magnetized barrier that deflects incoming charged particles. Cosmic rays, being charged particles, would follow magnetic field lines. A strongly compressed magnetic boundary could redirect them away before they enter. The second theory involves galactic winds. The center of the galaxy produces powerful outflows of gas and energy, material ejected by supernovae, stellar winds from massive stars, and energy from the black hole all push gas outward from the core at high speeds. Some researchers suggest this outward wind acts like a current pushing upstream against any incoming particles, making it effectively impossible for outside cosmic rays to flow in against the current. Both theories are plausible. Neither has been confirmed. The barrier exists. That much is certain. Why it exists, and what maintains it, remains an open question. And the particles it produces on the inside are generating a glow that has confused astronomers for over a decade. Before unpacking what the invisible barrier means, it helps to understand exactly what it is keeping out. Cosmic rays sound like science fiction. They are completely real, and they are passing through your body right now. A cosmic ray is a high-energy particle traveling through space at close to the speed of light. Most are protons, the positively charged particles that make up the core of atoms. Some are heavier atomic nuclei, like the cores of helium or iron atoms, stripped of their electrons and launched into space. A small fraction are electrons or other particles. All of them are moving fast, extremely fast. The most energetic cosmic rays ever detected carry so much energy that physicists gave them a nickname. They called the most powerful one the "Oh my God" particle. Discovered in 1991, that single proton carried as much kinetic energy as a baseball traveling at 50 miles per hour. The same energy packed into something smaller than an atom. It should have been slowed down by the background radiation filling the universe. The fact that it arrived with that energy intact meant it came from somewhere relatively nearby in cosmic terms, and it was moving at a speed so close to the speed of light that any difference was essentially unmeasurable. Most cosmic rays are less extreme, but they are still moving at speeds that make them genuinely dangerous over long periods of exposure. On Earth, the atmosphere absorbs most of them before they reach the ground. Astronauts in orbit, or anyone traveling beyond Earth's magnetic field, receive significantly higher doses. Planning a long-duration mission to Mars requires serious shielding because the cosmic ray environment in deep space poses a real health risk over months of travel. In space, these particles travel freely. They pass through gas clouds, through magnetic fields of moderate strength, and through the vast empty distances between stars without much trouble. That is why the wall at the galactic center is so puzzling. The central molecular zone should be flooded with cosmic rays. The rest of the galaxy is. The galactic center itself produces them in enormous quantities, from supernovae, from the activity around the black hole, from rapidly rotating dead stars. Those locally produced cosmic rays flow outward just fine, but the ones coming in from outside the zone? Blocked. The Fermi telescope measured the density of cosmic rays inside and outside the central molecular zone and found a sharp drop at the boundary. This is called a cosmic ray gradient, and it is steep enough to be unmistakable. The wall is real. Here is why this matters beyond just the galactic center. Cosmic rays play a role in the chemistry of gas clouds. They ionize gas, stripping electrons from atoms and triggering chemical reactions that would not otherwise occur. They influence how gas clouds cool and condense into new stars. If the central molecular zone is shielded from outside cosmic rays, its internal chemistry operates differently than similar gas clouds elsewhere in the galaxy. The star formation happening inside that zone might follow different rules. The molecules forming inside that cloud are shaped by a different radiation environment. The wall does not just block particles, it creates a separate chemical world inside the galactic center, one that operates under conditions found nowhere else. And the energy produced inside that world glows in a way that has been impossible to explain for 15 years. Two theories compete to explain the invisible wall around the galactic center. The first one involves magnetic fields, and to understand why scientists take it seriously, you need to understand how strange the magnetic environment at the galactic core actually is. The Milky Way, like most galaxies, has a magnetic field running through it. Throughout most of the galaxy, this field is relatively weak, far weaker than the magnet on your refrigerator. It spans enormous distances, threading through gas clouds and open space, gently nudging charged particles along its lines. For most of the galaxy, this field is a minor player. The galactic center is a completely different environment. The density of stars near the core is enormous. In our part of the galaxy, the nearest star to the Sun is about 4 light-years away. Near the galactic center, stars are packed close enough that the nearest neighbors might be separated by only a few weeks of light travel. That density means far more stellar activity, more stellar winds, more supernovae, more ionized gas. All of that generates stronger magnetic fields. The galactic center also has Sagittarius A star actively driving energetic outflows. Material swirling near the black hole generates magnetic fields through a process similar to what happens inside the sundae. Charged material moving in a curved path creates and amplifies magnetic fields. The more chaotic and energetic the motion, the stronger the resulting field. Measurements of the galactic center region show magnetic field strengths roughly 1,000 times higher than the galactic average. These fields are tangled, compressed, and constantly shifting as the gas around the core churns and flows. The magnetic barrier theory proposes that at the edge of the central molecular zone, these strong fields from the center meet the weaker fields from the outer galaxy. At that boundary, the stronger inner fields compress into a wall. Cosmic rays, being charged particles, follow magnetic field lines. When they hit a compressed magnetic boundary, they get redirected. They curve away from the zone and flow around it rather than through it. Think of it like a river hitting a concrete dam. The water does not stop entirely. It piles up, spreads sideways, and finds other paths. The cosmic rays hitting the compressed magnetic wall would behave similarly. They flow around the boundary rather than punching through it. This theory is supported by observations of the magnetic field structure near the galactic center. Scientists using radio telescopes have mapped the field orientation and found that it does run perpendicular to the galactic plane in the central region, forming a kind of vertical wall consistent with what the barrier theory predicts. But there are problems with this explanation. The magnetic fields at the boundary are not perfectly uniform. They show turbulence and gaps. A purely magnetic barrier with that much structural noise should leak. Some cosmic rays should find their way through. The measurements from Fermi suggest the barrier is sharper and more complete than a turbulent magnetic boundary would produce, which brings scientists to the second theory, one that involves the center of the galaxy actively pushing back against the rest of the universe. The second explanation for the cosmic ray barrier is more dramatic than the magnetic field theory. It proposes that the galactic center is not just blocking particles, it is actively blowing them away. The center of the Milky Way is not quiet. The black hole, the massive stars, and the constant cycle of supernovae in the central molecular zone all pump energy into the surrounding gas. That energy has to go somewhere. A significant portion of it goes outward, driving a powerful stream of gas and particles away from the core and out into the wider galaxy. This is called a galactic outflow, and it is a confirmed feature of the galactic center environment. Think of it as a wind. The galactic center generates a constant outward push of hot, fast-moving gas. This wind does not blow in one direction the way wind on Earth does. It expands outward in all directions from the center. Material ejected by supernovae, heated gas accelerated by the black hole's energy, stellar winds from hot, massive stars near the core, all of it flows outward at high speeds. The galactic wind hypothesis says this outward flow creates a natural barrier. Cosmic rays traveling inward from the outer galaxy are charged particles moving through space. When they hit a fast-moving wind of hot gas blowing in the opposite direction, the wind can slow them, scatter them, or simply push them back before they penetrate into the central molecular zone. The effect is directional. Particles produced inside the central molecular zone flow outward with the wind, gaining speed and escaping easily. Particles trying to travel inward from outside have to fight the current. The wind acts like a one-way valve. Things get out. Few things get in. This explanation accounts for something the magnetic field theory struggles with. The barrier is observed to be asymmetric. The cosmic ray gradient is steeper on certain sides of the central molecular zone than others. A purely magnetic barrier would tend to be more uniform. But if the barrier is driven by a wind, then differences in the wind's speed and direction at different points around the zone would naturally produce an uneven boundary. The data fits better. The galactic wind hypothesis also connects to a larger structure that astronomers have confirmed above and below the galactic plane. Two enormous bubbles of hot gas, each stretching tens of thousands of light-years above and below the Milky Way, were discovered by the Fermi telescope in 2010. These Fermi bubbles, as they are called, are almost certainly the product of past or ongoing galactic outflows from the center. The same wind driving the cosmic ray barrier at the boundary of the central molecular zone may be the local manifestation of the same energy system that inflated those massive bubbles. But even the galactic wind hypothesis has unresolved problems. The wind speed measured near the boundary does not appear to be fast enough in all directions to fully explain the sharpness of the cosmic ray cutoff. Something else may also be contributing. The two theories might both be partly right, with magnetic compression and galactic wind working together to maintain the barrier. Neither explanation has been confirmed as the complete answer. The wall stands. The reason it stands is still being debated, and the energy being produced inside that wall is causing an even bigger argument, one that could end with the discovery of dark matter. In 2009, the Fermi Large Area Telescope was scanning the galactic center when it detected something strange. A glow of gamma rays spreading outward from the core in every direction, smooth, uniform, and centered precisely on Sagittarius A star. Gamma rays are the most energetic form of light. A single gamma ray photon carries millions of times more energy than a photon of visible light. They are produced in extreme environments, nuclear reactions, exploding stars, particle collisions at energies that physicists can barely achieve in their largest accelerators. Finding a gamma ray glow at the galactic center was not surprising. The center is an extreme environment. What was surprising was the shape and the scale. This glow stretched roughly 5,000 light-years in every direction from the core. It was spherical, consistent across all directions, and surprisingly smooth. The spectrum of the gamma rays, meaning the range of energies they carried, did not match any known galactic source. Exploding stars produce gamma rays. Dead spinning stars, called pulsars, produce gamma rays. Jets from active black holes produce gamma rays. But all of those sources have characteristic signatures. This glow did not match any of them. Scientists called it the Galactic Center Excess. The name is deliberately dry. Behind the dry name is one of the most heated arguments in modern astrophysics. The excess produces gamma rays at a specific energy range, around a few 100 million electron volts. That specific energy level is highly significant. Theoretical models of dark matter, built decades before this glow was ever detected, predicted that if dark matter particles annihilated each other, the collision would produce gamma rays at almost exactly this energy level. Dark matter is the invisible substance that makes up roughly 85% of all matter in the universe. It has mass. It exerts gravity, but it does not emit light, reflect light, or interact with normal matter in any way that we can currently detect, except through gravity. Every major galaxy is embedded in a halo of dark matter far larger than the visible stars. The center of a galaxy, where gravity is strongest, should have the highest concentration of dark matter anywhere in that galaxy. If dark matter particles can collide and destroy each other when they meet, the galactic center is the place in the Milky Way where that would happen most often. And if it does happen, the energy released would come out as gamma rays, the exact kind the Fermi telescope was now seeing. The match between the observed glow and the theoretical dark matter prediction was striking enough to generate serious scientific excitement. Papers were published, conference talks filled rooms. Some physicists began cautiously suggesting that the galactic center excess might be the first direct observational signature of dark matter ever. That would be one of the biggest discoveries in the history of science. But before anyone could celebrate, a second explanation arrived, one that fit the data equally well, one that required no new physics at all, just an enormous hidden population of dead stars. If dark matter particles annihilate each other at the galactic center, the gamma-ray glow makes complete sense. The numbers line up, the energy spectrum matches, the spatial distribution fits. This theory, called dark matter annihilation, would explain the galactic center excess without requiring any unknown gamma-ray sources. Here is how it works. Dark matter particles, whatever they actually are, have mass and they have gravity. They are pulled toward each other the same way all matter with mass is pulled together. At the center of the galaxy, where the gravitational well is deepest, dark matter should be densest, packed tightly enough. These particles would occasionally collide directly with each other. When a dark matter particle meets its own antiparticle, or when two dark matter particles interact in the right way depending on what they are made of, the collision converts their combined mass into energy. This is the same basic process as matter-antimatter annihilation, something well understood in particle physics. The energy comes out in the form of other particles, including gamma rays. The specific type of dark matter particle most consistent with the galactic center excess is called a weakly interacting massive particle, often shortened to the letters WIMP. Theoretical physicists proposed this kind of particle decades before the Fermi telescope existed. The mass range and interaction strength that would make these particles annihilate and produce the observed gamma-ray spectrum are exactly what the theories predicted. This is called a smoking gun in science. When a predicted phenomenon shows up in the exact location, at the exact energy, with the exact spatial distribution that theory said to look for, that is extraordinary evidence. But extraordinary evidence requires extraordinary scrutiny, and the scrutiny revealed a problem. The gamma-ray signal from the galactic center excess is smooth, suspiciously smooth. Dark matter, distributed throughout the galactic halo in a roughly spherical shape centered on the black hole, would produce a smooth glow. That part fits, but the galactic center is also filled with known sources of gamma rays that are not smooth at all: pulsars, supernovae remnants, gas clouds lit up by cosmic rays. These sources are clumpy and uneven. When scientists tried to subtract all the known sources from the Fermi data to isolate the excess, the remaining glow appeared smooth. That smoothness was initially taken as support for the dark matter interpretation. Then came a study using a different statistical technique to analyze the same data. Instead of looking at the average brightness across the glow, researchers examined the statistical texture of the signal. They found hints that the emission might come from many separate faint point sources too dim to resolve individually, but collectively producing the appearance of a smooth glow. That finding pointed away from dark matter and toward a different culprit entirely, one hiding in plain sight inside the galactic center, spinning so fast it makes a neutron star look leisurely. 100,000 dead stars, all spinning, all hidden, all possibly producing the glow that some scientists thought was proof of dark matter. That is the alternative explanation for the galactic center excess, and it fits the data almost as well as the dark matter theory. Pulsars are the collapsed cores of massive stars that have exploded as supernovae. When a star with roughly 8 to 20 times the mass of our Sun reaches the end of its life, it detonates. The outer layers blast outward, the core collapses inward under gravity. Electrons and protons get crushed together into neutrons. The result is a neutron star, an object roughly the size of a city packed with more mass than the Sunday. Some neutron stars spin very fast, up to several hundred rotations per second, and as they spin, their intense magnetic fields sweep beams of high-energy radiation around like a lighthouse. When one of those beams sweeps across Earth, we detect a rapid, regular pulse of radio waves or gamma rays. That is a pulsar. A specific class called millisecond pulsars spin the fastest. They have been spun up to extreme rotation speeds by pulling material from a companion star over long periods of time. They are very old, very stable, and they emit gamma rays at specific energies. Here is the key detail. The gamma ray spectrum, produced by a population of millisecond pulsars, matches the spectrum of the galactic center excess, closely enough that the two are very hard to tell apart. The galactic center has been producing new stars, going supernova, and building up stellar remnants for billions of years. The density of stars in that region is high enough that binary star systems, the fuel source for millisecond pulsars, form regularly. A large population of millisecond pulsars in the galactic center is expected by stellar evolution models. The question is how large that population is. Some estimates suggest as many as 100,000 millisecond pulsars could be hidden inside the central molecular zone. Individually, they are too faint to resolve from Earth's distance, but collectively, their combined gamma-ray emission would look exactly like the smooth, spherically distributed glow that Fermi detected. The two explanations sit side by side: dark matter, annihilation, or 100,000 pulsars. Both produce the right kind of gamma rays. Both produce the right spatial distribution. Both are physically plausible. One would be the greatest discovery in scientific history. The other would be a remarkable but ordinary feature of stellar evolution in a dense galactic environment. The current data cannot choose between them, and the reason it cannot is genuinely frustrating. Two explanations. Both fit. One is a population of dead stars. The other is the first confirmed detection of dark matter destroying itself at the center of the galaxy. Scientists have spent over a decade trying to distinguish between them. The problem is not that they lack data. The problem is that the two signals are nearly identical. Here is why separating them is so difficult. Both dark matter annihilation and millisecond pulsars produce gamma rays in the same energy range. Both produce emission that is roughly spherically symmetric around the galactic center. Both have spatial profiles, meaning the way the brightness changes with distance from the center, that are consistent with the Fermi observations. The only way to tell them apart would be to find a difference in the statistical texture of the emission, or to resolve individual pulsars, or to find a signal from another galaxy where the same conditions exist. The texture approach has been tried. The results are contested. One group of researchers used a statistical method to show that the excess has the statistical properties expected from millions of faint point sources. which would support the pulsar explanation. A different group used a different method and argued the signal is consistent with a truly smooth, diffuse emission, which favors dark matter. The two analyses used the same Fermi data and reached opposite conclusions. The difference came down to how they modeled the background emission and what assumptions they made about the galactic center environment. That background modeling problem is serious. The galactic center is one of the most complicated regions in the sky for gamma-ray astronomy. Known sources overlap. The diffuse emission from cosmic rays interacting with gas is enormous. Subtracting all of that to isolate the excess requires assumptions. Different assumptions produce different answers. Resolving individual pulsars would settle the debate. If telescopes could see distinct point sources of gamma rays inside the galactic center, each one matching the signature of a millisecond pulsar, the pulsar explanation would win. Current telescopes cannot achieve that resolution at the distance of the galactic center. The next generation of gamma-ray telescopes, currently in development, might have enough sensitivity and resolution to find individual pulsars in that region. If they do, the dark matter interpretation dies. If they do not find individual pulsars, where the models predict they should be, dark matter becomes significantly more likely. Looking at other galaxies with similar properties offers another test. Dwarf galaxies orbiting the Milky Way contain very few stars and almost no pulsars, but they contain a lot of dark matter relative to their total mass. If dark matter annihilation is producing the galactic center excess, those dwarf galaxies should also show a gamma-ray excess proportional to their dark matter content. Searches have found hints, but no definitive signal yet. The debate is not stalled because scientists are not looking hard enough. The debate is stalled because the observations at this distance simply cannot separate the two explanations with current instruments. This situation has a name in science. It is called a degeneracy. Two models predict the same observable outcome. The data cannot choose between them. Until better tools arrive, the galactic center excess sits in a category that is genuinely uncomfortable for physics, confirmed as real, unexplained as to origin. Potentially the most important discovery in the history of science. Potentially a very large collection of spinning dead stars. Both possibilities remain alive. And sitting in the same region of space, buried in that same crowded galactic center, is something that does not fit either theory. Something sending out signals nobody predicted, at times nobody can anticipate. Deep inside the galactic center, something is broadcasting. It switches on without warning. It goes dark without explanation. And in the years since its discovery, no one has identified what it is. Astronomers discovered the signal in 2021 while surveying the galactic center with the Meerkat radio telescope array in South Africa. The signal came from a point source, meaning a compact, localized object rather than a diffuse cloud. It flickered, it pulsed, it produced radio waves unlike anything catalogued before. The team that found it gave it an informal nickname based on the initials of the lead researcher who noticed it. They called it Andy's object. The formal designation is less memorable. The nickname stuck. What makes Andy's object different from other variable radio sources in the galaxy starts with polarization. Radio waves, like all electromagnetic waves, oscillate as they travel. Normally, those oscillations happen in random orientation. Polarized radio waves all oscillate in the same plane, or they rotate in a consistent spiral pattern as they travel. Producing highly polarized radio waves requires a very specific environment. Specifically, a powerful magnetic field that forces the waves into alignment as they are emitted. Andy's object produces radio waves that are almost completely polarized, not partially, almost entirely. That level of polarization points to an extremely strong and organized magnetic field at the emission site. Whatever is generating the signal sits inside a magnetic environment far more intense than what surrounds most known stellar objects. Known sources of polarized radio emission include pulsars, magnetars, which are neutron stars with especially extreme magnetic fields, and jets from active black holes. None of those matches the behavior pattern of Andy's object. Pulsars pulse with clockwork precision. Their timing is so reliable that astronomers use them as cosmic clocks. Andy's object turns on and off with no predictable rhythm. It is active for a period, then vanishes completely, then returns. The gaps between active periods vary. The duration of the active phases varies. No underlying clock has been found in the data. Magnetars do produce erratic signals, but they also produce X-ray bursts during active phases. Telescopes scanning the galactic center for X-rays during Andy's object's active periods have detected no matching X-ray signal. That rules out a standard magnetar. An active galactic jet would produce emission across a wide range of wavelengths simultaneously. Andy's object shows up only in radio. Its signature has not been confirmed in any other wavelength band. The object sits in a region of the galactic center with extremely high stellar density and intense magnetic fields. Those conditions could plausibly produce something new, a stellar object or remnant with properties that fall between the known categories. A team of researchers proposed that Andy's object could be a new class of radio transient, a category of object that only recently began to be systematically catalogued. Several other unpredictable radio sources have been found in the last few years using sensitive new radio telescope arrays. Some researchers think these may all be related, part of an emerging class of objects with properties that current models of stellar physics did not anticipate. The signal from Andy's object is real. Its polarization is confirmed. Its irregular timing is confirmed. Its origin and mechanism remain entirely unknown. And the clue hiding inside those polarized waves points to something about the galactic center's magnetic environment that goes far beyond one mystery object. The fact that Andy's object produces highly polarized radio waves is not just a curiosity, it is a clue. And the clue points towards something about the galactic center that makes the entire region stranger than it already appeared. Start with what polarization actually means at the source. When a charged particle, like an electron, accelerates through a magnetic field, it emits radiation. If the magnetic field is tangled and disorganized, the radiation comes out with random polarization, waves oscillating in all directions. If the magnetic field is strong, ordered, and consistent, the radiation comes out highly polarized, waves locked into a specific orientation or spiral. The degree of polarization in Andy's object's signal is high enough to indicate a magnetic field at the emission source that is both powerful and organized. The field lines are running in a coherent direction. Something at that location is generating or sustaining a magnetic structure with real internal order. Here is where it gets deeper. As radio waves travel through space, they pass through plasma, ionized gas, which contains free electrons. A magnetic field threaded through that plasma causes the polarization angle of the radio waves to rotate. The amount of rotation tells you something about the strength of the magnetic field along the path the waves traveled and the density of the plasma they passed through. Astronomers call this effect Faraday rotation, named after the scientist who first described the underlying physics. Measuring the Faraday rotation of Andy's object's signal reveals information about everything the radio waves passed through between the object and Earth. That path runs straight through the galactic center. The rotation values measured from Andy's object are extremely high, among the largest ever recorded for any source in the Milky Way. That means the radio waves traveled through a region of exceptional magnetic field strength and plasma density. The galactic center is already known to host strong magnetic fields, but the Faraday rotation from Andy's object suggests the fields in its immediate vicinity are even more intense than the surrounding region. Something local to that object is amplifying or concentrating the magnetic environment. This matters beyond just Andy's object itself. The galactic center magnetic field plays a role in almost every process happening there. It influences how gas clouds move and collapse. It affects how cosmic rays scatter and travel. It shapes the outflows from the black hole. It may contribute to the cosmic ray barrier. Understanding the magnetic structure near Andy's object could shed light on the larger magnetic architecture of the entire central region. The problem is that mapping the magnetic field of the galactic center in detail requires many sources with measurable Faraday rotation spread across the region. Andy's object provides one data point, a very striking one, but one among many needed to build a complete picture. Radio telescopes scanning the galactic center continue to collect data whenever Andy's object activates. Each active period produces new measurements of the polarization and Faraday rotation. Those measurements are being compiled alongside data from other compact radio sources in the same region, but the signal keeps cutting out, and the silence between the active phases carries its own kind of mystery. Andy's object does not follow a schedule. That single fact places it outside every category of known repeating astronomical radio source. Pulsars pulse. Their timing is so stable that the most precise ones lose less than 1 second every 300 million years. Rotating radio transients, a class of neutron stars discovered in the early 2000s, pulse irregularly, but still show a detectable underlying period when enough data is accumulated. Magnetar outbursts follow a general pattern tied to the decay of their extreme magnetic fields over months to years. Fast radio bursts, one of the newest and most puzzling categories of cosmic signals, repeat in some cases with quasi-periodic timing. Andy's object does none of these things. Its active phases have lasted anywhere from weeks to months. Its silent phases vary just as widely. No period has been extracted from the data. No model of a known stellar object produces this kind of timing behavior. When Andy's object goes quiet, it goes completely quiet. The radio emission drops below the detection threshold of the Meerkat array. Whether it is actually producing no emission during those periods, or producing emission below the instrument's sensitivity, is unclear. A faint, persistent signal, too dim to detect, would look identical to true silence in the current data. The return to activity shows no warning. One observation session reveals nothing. The next reveals a bright, highly polarized source in the same position. The transition between states appears abrupt, though the cadence of observations means a gradual change could be happening between sessions without being caught. Several explanations have been explored. One involves a geometric effect called scintillation. Radio waves traveling through the turbulent plasma of the galactic center can brighten and fade due to interference patterns, similar to how stars twinkle in Earth's atmosphere. If Andy's object is a faint but constant emitter, the interstellar turbulence between it and Earth could cause its apparent brightness to swing from detectable to undetectable and back. This would create the impression of an object switching on and off when it is actually always transmitting. That scintillation explanation has not been ruled out, but the degree of variation observed in Andy's object is difficult to explain through scintillation alone. The signal changes too dramatically, and the polarization properties change between active phases in ways that simple scintillation would not produce. Another possibility is accretion, the process of a compact object pulling material from a companion star or surrounding gas cloud. When material falls onto a neutron star or small black hole, it can produce bursts of radio emission. If Andy's object is accreting gas from an irregular supply, the radio emission would switch on when gas arrives and switch off when the supply runs dry. The galactic center is full of gas clouds and stellar winds, making this a plausible fuel source. The honest scientific position on Andy's object is this: the signal is real, the polarization is extraordinary, and the timing behavior is unprecedented. The mechanism is unknown. The object class is unidentified. It may represent something entirely new. Somewhere in the galactic center, something is sending out messages. And right now, nobody knows who or what is writing them. Everything discussed so far about the galactic center assumes one thing: that the object at the very center, the anchor of all the strange orbits and extreme physics, is a black hole. Specifically, a supermassive black hole with a mass of about 4 million times the Sunday. A team of astrophysicists published a paper challenging that assumption directly. Their proposal was striking. What if there is no black hole at the center of the Milky Way? What if the gravitational anchor pulling everything into those extreme orbits is instead a dense concentration of dark matter? The proposal is called a dark matter spike or dark matter core model. It builds on the fact that dark matter clusters around gravitational centers. Every large galaxy is embedded in a vast halo of dark matter. That halo concentrates more densely toward the center of the galaxy, following a profile that theoretical models have described for decades. At the very core of that density profile, the concentration of dark matter could become extreme enough, the paper argues, to mimic the gravitational effects of a supermassive black hole. The key measurement driving belief in the black hole model is the behavior of stars near the galactic center. Those stars follow orbits that require a central mass of roughly 4 million solar masses. That mass is confirmed. The question is, what form it takes. A supermassive black hole packs that mass into a region smaller than the solar system. Extremely dense, extremely compact. A dark matter core would spread that same mass across a somewhat larger volume, but still compact enough to produce the same stellar orbits at the distances being observed. The orbits of most tracked stars near the center cannot distinguish between the two possibilities. The gravitational pull is the same either way at the distances those stars travel, but certain stars that pass closer to the center might show differences. A black hole produces specific relativistic effects on nearby objects that a dark matter concentration would not replicate exactly. The shift of S2's light toward the red end of the spectrum during its closest approach, the gravitational redshift detected in 2018, matched the black hole prediction. That observation is difficult but not impossible for some dark matter core models to accommodate. The Event Horizon Telescope image from 2022 shows a shadow with the correct size and shape for a 4 million solar mass black hole. A dark matter core would not produce the same distinct shadow. That image is the strongest evidence against the dark matter core model and the strongest direct evidence for an actual black hole. Most astronomers consider the black hole model confirmed to a high degree of certainty. The dark matter core alternative is a minority view, but the paper that proposed it is not fringe science. It was published in a peer-reviewed journal. The mathematics behind it are internally consistent, and it highlights something worth acknowledging. There are specific stars near the galactic center whose orbits do not fit the standard black hole model perfectly. Small deviations, residuals that require additional components in the model to explain. Whether those deviations point to dark matter, to smaller black holes, to measurement uncertainty, or to something else entirely, is not settled. The black hole is almost certainly there. The question of whether it is alone and whether dark matter plays a larger role in the central dynamics than the standard model accounts for remains genuinely open. The stars near the galactic center do not all behave the way the models expect. Some of them move in ways that require explanation beyond a single central black hole sitting alone in empty space. Start with speed. The stars closest to Sagittarius, A star, move extraordinarily fast. S2 reaches nearly 3% of the speed of light during its closest approach. Other members of the central S cluster have similar peak velocities. Those speeds are consistent with the gravitational pull of the central mass. No problem there. The problem lies in the orbital shapes and orientations. Stars in a stable system orbiting a single central object should, over long periods, have their orbits influenced by the combined gravity of everything around them. In a region as dense as the galactic center, those influences are significant. Close encounters between stars can slightly alter orbital paths. The combined gravitational effect of a dense cluster of stars and stellar remnants can cause orbits to precess, meaning the orientation of the ellipse slowly rotates over time. General relativity adds another layer of precession. Einstein's theory predicts that orbits in strong gravitational fields do not stay fixed. The ellipse itself rotates. For S2, this relativistic precession was confirmed for the first time in 2020. The orbit shifted by a small but measurable angle after one full trip around the black hole, exactly as general relativity predicted. But some stars near the center show precession rates or orbital inclinations that do not fit neatly into models that account for only the central black hole and the known stellar density. The discrepancies are small, but they are persistent across multiple independent analyses. One candidate explanation is a population of intermediate mass black holes orbiting the central supermassive one. Black holes with masses between 100 and 100,000 solar masses, too large to be ordinary stellar remnants, but far smaller than Sagittarius A star. If several of these exist close to the center, their gravity would perturb the orbits of nearby stars in ways that mimic what the observations show. Theoretical models predict that intermediate mass black holes could migrate inward over time due to a process called dynamical friction, gradually losing energy to the surrounding stars and sinking toward the center. No intermediate mass black hole has been directly confirmed near the galactic center, but the orbital data provides indirect evidence that something beyond the single central black hole is influencing nearby star motions. Another candidate is a distributed mass of dark matter clustered tightly around the core. If dark matter spikes toward very high density at the galactic center, it adds a gravitational component spread across a volume rather than concentrated at a point. That distributed extra gravity would affect stellar orbits differently than a point mass would, potentially explaining some of the observed deviations. The fast-moving stars near the galactic center are among the most precisely tracked objects in astronomy. The data covering them spans over 2 decades of continuous observation. That data confirms general relativity. It confirms the central mass, and it leaves behind residuals that the standard model, a lone supermassive black hole in an otherwise simple environment, cannot fully explain. Something else is there. The argument is over what. Dark matter shows up as an explanation for multiple mysteries at the galactic center: the gamma-ray glow, the orbital deviations, the possible alternative to the black hole model. To understand why scientists take it seriously as a factor in all of these, it helps to understand what dark matter actually is and why it has to exist. The story starts with a Swiss astronomer named Fritz Zwicky in 1933. Zwicky was studying a large cluster of galaxies and measuring how fast the individual galaxies moved within the cluster. He applied a basic principle of physics. The speed at which objects orbit a gravitational center tells you how much mass that center contains. The faster the orbit, the more mass. The galaxies in the cluster were moving far too fast to be held together by the visible mass of the stars within them. If only the visible stars contributed their gravity, the cluster should have flown apart long ago. Zwicky proposed that a large amount of invisible mass, which he called dark matter, must be providing additional gravity to hold everything together. The scientific community largely ignored him for decades. Then, in the 1970s, an astronomer named Vera Rubin made the same discovery on a smaller scale. She measured how fast stars at different distances from the center of a galaxy rotated around it. Physics predicts that stars far from the center, where most of the visible mass is concentrated, should rotate slowly, the same way outer planets in our solar system orbit the sun more slowly than inner ones. Rubin found the opposite. Stars at the outer edge of galaxies orbited just as fast as stars near the center. The rotation curves were flat when they should have been declining. The only explanation that worked was a halo of invisible mass surrounding each galaxy, extending far beyond the visible stars, providing extra gravity that kept the outer stars moving fast. That halo is dark matter. Since Rubin's work, dark matter has been confirmed through multiple independent methods. Gravitational lensing, where massive invisible structures bend light from objects behind them. The large-scale structure of the universe, where the pattern of galaxy clustering matches simulations that include dark matter and fails to match ones that exclude it. The cosmic microwave background, the afterglow of the Big Bang, whose detailed temperature patterns require dark matter to explain their shape. Dark matter makes up roughly 85% of all matter in the universe by mass. Ordinary matter, everything made of atoms, everything we can see, touch, or detect directly, accounts for only 15%. What dark matter is made of remains unknown. The leading candidates are particles that interact with gravity, but not with light or ordinary matter, through the other fundamental forces. Weakly interacting massive particles have been the top candidate for decades, though experiments designed to detect them directly have found nothing conclusive. Other candidates include axions, sterile neutrinos, and primordial black holes formed in the early universe. Whatever dark matter is, it concentrates at the centers of galaxies. The galactic center of the Milky Way should have more dark matter per unit volume than anywhere else in the galaxy. That concentration is why dark matter keeps appearing as a candidate explanation for so many galactic center anomalies. It is everywhere. It drives the structure of the cosmos, and we have never once touched it directly. The galactic center excess in gamma rays might be the first direct observational signature of dark matter annihilation. If that theory is confirmed, the consequences for science would extend far beyond one astrophysics paper. They would cascade through particle physics, cosmology, and fundamental physics in ways that would take decades to fully work out. Here is why the stakes are so high. Dark matter has been inferred through its gravitational effects for nearly a century. But gravitational effects alone cannot tell us what dark matter is made of. They tell us the mass is there. They do not tell us the particle. Every experiment designed to catch dark matter directly, to detect a particle of it passing through a detector, to produce it in a particle accelerator, to see it annihilating in a telescope, has returned either a null result or a disputed signal. The current state of dark matter research is this. We know it exists. We know roughly how much of it there is. We know where it tends to accumulate. We have 0 confirmed direct detections of a dark matter particle. If the galactic center excess is confirmed as dark matter annihilation that changes everything, it would tell us the mass of the dark matter particle, because the energy of the gamma rays constrains the mass of the annihilating particles directly. It would tell us something about the interaction strength between dark matter particles, because the brightness of the glow constrains the rate of annihilation. It would give theorists the first hard experimental data to build a particle physics model of dark matter from the ground up. Every model of particle physics beyond the standard model would need to accommodate the result. The most popular class of candidate particles, weakly interacting massive particles, would either be confirmed or ruled out, depending on whether their predicted properties match the galactic center signal. The implications for cosmology are equally large. Dark matter does not just sit in galaxy halos. It structured the entire universe. The way galaxies formed, the way galaxy clusters assembled, the way the large-scale web of the universe grew after the Big Bang, all of that was shaped by dark matter. Knowing what dark matter actually is would allow cosmologists to model the early universe with dramatically greater precision. Open questions about the first stars, the first galaxies, and the physics of the very early universe all depend on the properties of dark matter. And if dark matter annihilates at the galactic center, it annihilates everywhere that dark matter concentrations exist. Every galaxy with a dense core should show a similar glow. Every dwarf galaxy, every dark matter filament in the cosmic web. Astronomy would gain a new tool, a new kind of light to map the invisible architecture of the universe. Confirming this would rank among the most significant scientific discoveries in history, on par with the confirmation of the Higgs boson, possibly above it. The next generation of gamma-ray telescopes and the continued analysis of Fermi data represent the current best hope for settling the question. If they find individual pulsars filling the galactic center, the dark matter interpretation dies. If they find no pulsars, the case for dark matter strengthens dramatically. Both outcomes would be historic. One would end a debate, the other would begin an era. Pull back from the black hole and the stars orbiting it, and you enter a region of space unlike anything else in the Milky Way. A vast, dense cloud of gas and dust surrounding the galactic core, stretching roughly 900 light-years across its longest dimension. Astronomers call it the central molecular zone. To get a sense of its scale, the distance from Earth to the nearest star, Proxima Centauri, is about 4 light-years. The central molecular zone is over 200 times wider than that distance. It is enormous, and it is packed with material in quantities that challenge easy comparison. The cloud contains roughly 60 million solar masses of gas. That is enough raw material to build 60 million stars the size of our Sun. Most of that gas is molecular hydrogen, the most common molecule in space. But the central molecular zone also hosts an unusually rich chemistry, with complex molecules forming inside dense pockets of gas. Normally, complex molecules in space are fragile. Ultraviolet light from nearby stars breaks them apart. Cosmic rays ionize the gas, disrupting molecular bonds. In most regions of the galaxy, this keeps the molecular complexity relatively low. Simple molecules dominate, but the central molecular zone operates under different conditions. The high density of the gas provides shielding from ultraviolet light in many regions. The cosmic ray barrier, which reduces the inflow of cosmic rays from the outer galaxy, changes the ionization environment inside the zone, and the extreme conditions near the galactic center, including turbulence driven by the black hole's gravity and the dense stellar population, stir the gas constantly, mixing material and driving chemical reactions in ways that more quiescent regions cannot replicate. Scientists have detected dozens of complex molecules inside the central molecular zone, including ones that serve as precursors to amino acids, the building blocks of proteins. This does not mean life is forming at the galactic center. The radiation environment is far too hostile for biology. But it means the chemistry happening inside the zone is producing molecular complexity at a level that continues to surprise researchers. The gas in the zone is also hot, extremely hot for a molecular cloud. Typical molecular clouds in the outer galaxy have temperatures close to absolute zero. The central molecular zone's gas sits at temperatures many times higher, driven by the turbulence and energy input from the galactic center environment. That elevated temperature affects how the gas behaves, how it moves, and whether it can collapse to form new stars. Star formation inside the central molecular zone is surprisingly suppressed given how much gas is available. The gas is there. The mass is there. But turbulence keeps the clouds stirred up and prevents them from collapsing into new stars at the rate that the available material would suggest. The galactic center has enough gas to form millions of new stars, but forms far fewer than expected. Understanding why is an active area of research. The zone sits at the crossroads of every major process happening in the galactic center. The black hole, the strange orbiting objects, the cosmic ray barrier, the gamma-ray glow, all of them interact with the central molecular zone in some way, and the energy pouring out of the center does not stay contained. Some of it escapes, dramatically. The galactic center does not hold its energy, it releases it, in enormous quantities, through outflows of hot gas and radiation that shoot away from the core and travel for thousands of light-years before the energy finally disperses. These outflows come from multiple sources working together. The most direct driver is Sagittarius A star itself. Even in its current relatively quiet state, the black hole at the galactic center releases energy as material falls toward it. Gas spiraling into the black hole heats up dramatically as it compresses. Before crossing the event horizon, some of that infalling material gets redirected by magnetic fields into powerful jets or winds, blasting outward along the poles of the black hole's rotation axis. The central stellar population also contributes massively. The galactic center contains a dense cluster of young, massive, hot stars. Stars many times more massive than the Sun burn through their fuel rapidly and produce powerful stellar winds throughout their lifetimes. When they die in supernova explosions, they release enormous amounts of energy into the surrounding gas. With so many massive stars packed into a small region, the combined energy input from their winds and eventual explosions creates a sustained outflow from the central region. All of this energy drives gas outward. The outflow carries both hot plasma and magnetic fields, threading energy into the surrounding medium as it expands. Within a few hundred light years of the core, this outflow is already powerful enough to shape the structure of the central molecular zone, which is why scientists consider the galactic wind as a possible contributor to the cosmic ray barrier. But the outflow does not stop there. It keeps going. Material and energy from the galactic center fountain upward and downward, perpendicular to the flat disk of the Milky Way. As it rises, it carries heat, cosmic rays, and magnetic fields into the region above and below the galaxy called the halo. This upward flow of energy has been shaping the environment of the Milky Way's halo for millions of years. The consequences of this energy export are observable. The chemistry and temperature of gas in the inner halo above the galactic center differs from similar gas in other parts of the halo, reflecting the energy input from the core. The magnetic field structure threads outward from the galactic center, following the direction of the outflow and leaving a detectable signature in the radio wave emission from the region. And, at a much larger scale, this outflow has inflated two structures so enormous that they were not even discovered until satellite telescopes got above Earth's atmosphere and looked at the full sky with fresh eyes. Those structures are so large that if they were visible to the human eye, they would cover a significant fraction of the entire night sky. And they have been sitting above and below our galaxy the whole time, completely invisible from the ground. In 2010, scientists analyzing data from the Fermi Large Area Telescope found something that should have been obvious long before. Two enormous structures ballooning out from the center of the Milky Way, one above the galactic plane and one below, perfectly symmetric, each one stretching roughly 25,000 light-years from top to bottom. Together, the pair spans about 50,000 light-years from end to end. They are called the Fermi bubbles, and they are gigantic. To understand their scale, the entire visible disk of the Milky Way is about 100,000 light-years across. Each Fermi bubble is roughly half that length in height. If you could see them from outside the galaxy, they would look like two enormous lobes attached to the center of a flat disk, like a peanut shape rotated sideways. From our position inside the galaxy, they extend far above and below our location, covering a huge portion of the sky when observed in gamma rays. The bubbles glow. They emit gamma rays and microwave radiation across their full extent. They are filled with energetic electrons, magnetic fields, and hot gas. The boundary between each bubble and the surrounding intergalactic medium is surprisingly sharp. There is a defined edge where the bubble material stops and the quieter surrounding gas begins. That sharp edge tells scientists the bubbles expanded relatively quickly and have been maintained against diffusion for some time. The origin of the Fermi bubbles is debated. The two leading explanations mirror the same basic question underlying many galactic center mysteries: active black hole or stellar processes. The black hole explanation proposes that Sagittarius A star went through a period of intense activity in the relatively recent past, perhaps a few million years ago. During that active phase, the black hole consumed a large amount of material and launched powerful jets of energy along its rotation axis. Those jets plowed into the surrounding gas, creating two cavities that expanded outward and are now observed as the bubbles. Evidence from X-ray observations of the gas around the bubbles supports the idea that something energetic expanded outward from the center relatively quickly, consistent with a jet-driven event. The stellar wind explanation argues that the combined effect of millions of years of stellar winds and supernovae from the dense star population at the galactic center could gradually inflate similar structures without requiring a past active black hole phase. Simulations show that sustained stellar energy injection into the galactic center can produce bubble-like structures over long timescales. Both models match the overall size and shape of the bubbles reasonably well. Distinguishing between them requires detailed analysis of the gamma-ray spectrum and polarization inside the bubbles, which ongoing observations continue to refine. What is certain is that the galactic center has been pumping energy outward for a very long time. Enough energy to inflate two structures, each the size of a small galaxy, hanging above and below the Milky Way, like a permanent record of the core's past behavior. That energy output raises a question that many people ask and that deserves a direct answer. Is any of this dangerous to us? The galactic center is violent. It contains a supermassive black hole. It blasts cosmic rays outward. It has inflated two structures the size of small galaxies above and below the Milky Way. Radio signals broadcast from unknown sources inside it. Strange objects orbit its core. Gamma-ray glows fill its surrounding region. And Earth sits 25,800 light-years away from all of it. That distance is the answer to most of the concern. The effects that would need to threaten life on Earth require either direct proximity to the galactic center or a cataclysmic event so powerful it could project destructive energy across the distance of the galaxy. The first condition is obviously not met. The second has not happened in Earth's history in any form that disrupted life. Cosmic rays from the galactic center do reach Earth. The cosmic ray flux at Earth's location includes particles that originated near the galactic center, mixed with cosmic rays from many other sources throughout the galaxy. The cosmic ray environment at Earth has been roughly constant throughout the history of complex life. It fluctuates, but no galactic center event in the past has been recorded as causing a mass extinction through increased cosmic ray flux. The Fermi bubbles extend roughly 25,000 light-years above and below the galactic plane. Earth sits in the galactic plane at a distance from the center that places it far outside the region directly swept by the bubble's edges. The gamma-ray and microwave emission from the bubbles contributes to the background radiation environment of the galaxy, but at Earth's distance and location, it is far below any level of concern. Flares from Sagittarius A star, the sudden brightenings of the black hole when material falls in, produce bursts of X-ray and radio emission. Even the largest detected flares from the galactic center have produced energy outputs far below what would be needed to cause detectable effects at Earth's distance. A truly enormous flare, larger than anything observed in the modern era, could potentially produce a measurable increase in gamma-ray flux at Earth. But the effect would be spread across a hemisphere of the sky, diluted by distance, and filtered by Earth's magnetic field and atmosphere. There is one scenario that astrophysicists consider on very long timescales. If Sagittarius A star underwent an extremely powerful episode of activity, producing jets as energetic as those seen in the most active galactic nuclei in other galaxies, the resulting blast could, in theory, project enough energy to influence conditions far across the Milky Way. But active galactic nuclei of that power are associated with black holes consuming material at rates far higher than anything currently measured or geologically recorded for our galactic center. The honest answer is that the galactic center is spectacularly dangerous to anything near it. At our current distance, it is a source of fascination and scientific data, not physical threat. The events happening at the core are, from our perspective, an extraordinarily detailed physics experiment playing out 25,000 light-years away. The danger is theoretical and distant. The mystery is real and immediate. And one aspect of that mystery involves what the galactic center might do in the future. Sagittarius, a star, is quiet right now. Relative to the most active galactic nuclei observed in other galaxies, our black hole barely whispers. But the galactic center carries evidence that this has not always been the case. And the data suggests the center can wake up. A few million years ago, something happened at the galactic center. The Fermi bubbles are the most dramatic evidence. Those structures represent an enormous release of energy from the core, enough to inflate two lobes of hot gas stretching far above and below the galaxy over a relatively short period in astronomical terms. Whether it was a jet-driven event from Sagittarius A star or a surge of stellar activity at the center, the energy output required was immense. More recently, in astronomical timescales, the galactic center showed signs of a past active period. X-ray and gamma-ray observations of gas clouds in the central molecular zone reveal a phenomenon called a light echo. Some clouds in the region glow with X-rays at exactly the intensity and spectrum you would expect if they were reflecting a past X-ray flare from Sagittarius A star. By tracing the geometry of the illuminated clouds and calculating how long the light took to reach them from the black hole's position, scientists estimated the timing of the original flare. The result pointed to an event roughly a few hundred years ago in which Sagittarius A star was millions of times brighter than it is today, a major feeding event. A brief but powerful eruption. The evidence for this is the X-ray light that bounced off the clouds and only now arrived at those clouds as the light front from the original eruption expanded outward. The clouds are currently illuminated. The source that lit them up has already gone quiet. Current observations show Sagittarius A star does flare regularly, multiple times per day in X-rays, with brightness jumping dramatically for short periods. These small flares are well documented. What triggers them remains incompletely understood. Most are probably caused by clumps of gas or plasma falling toward the event horizon. A much larger future eruption is consistent with everything the historical evidence suggests. The galactic center cycles through active and quiet periods. The current quiet period could last for millions of years, or something large could fall into the black hole relatively soon. The gas cloud G2 approached but survived in 2014. The gas it shed during that close pass continues falling toward the black hole in a stream. As that material arrives at the event horizon over coming years and decades, it may trigger a detectable increase in emission. Scientists have monitored the black hole carefully since the G2 passage for signs of feeding-related brightening. Any future major eruption would send radiation outward in all directions. From Earth's distance and with our atmosphere as shielding, even a large flare would be scientifically spectacular and practically harmless. It would, however, rewrite our understanding of how and when galactic centers become active. The galactic center is not frozen, it has a history, and that history points to a cycle of activity that the current quiet phase is simply part of. Every process in the universe has a place where it happens in its most extreme form. Stellar physics happens everywhere stars exist. But the most extreme stellar physics, the conditions where normal stars behave in ways they do not elsewhere, happens near the galactic center. Gravity physics operates throughout the universe, but the most extreme curvature of space, the conditions where general relativity produces effects large enough to measure clearly, happens near a 4 to million solar mass black hole. This is why astronomers and physicists treat the galactic center as a laboratory, not a lab they built, one the universe built for them. General relativity has been tested near the galactic center in ways that are impossible to replicate anywhere closer to Earth. The relativistic precession of S2's orbit, confirmed in 2020, tested general relativity in a gravitational field far stronger than any produced in the solar system. The gravitational redshift of S2's light confirmed another prediction of the theory. Together, these tests are among the strongest verifications of general relativity ever performed. Future observations will push further. As more stellar orbits are tracked with greater precision, any deviations from general relativity would become detectable. If the theory fails at some scale, the galactic center is one of the best places to find out. The physics of accretion, how matter falls onto a compact object and releases energy, operates at its most extreme near Sagittarius A star. Every flare, every quiet period, every measured variation in the black hole's brightness teaches physicists something about how accretion works in the strongest possible gravitational field. That knowledge applies throughout the universe, wherever black holes are consuming material. Plasma physics at the galactic center operates in magnetic field environments far beyond what any earthly laboratory can produce. the processes that accelerate cosmic rays to near light speed, that organize magnetic fields into coherent structures, that drive the jets and outflows. All of these are happening in real time at the galactic center. Observing them directly provides data that theoretical models of plasma physics cannot generate on their own. The chemistry of the central molecular zone tests astrochemistry, the study of how molecules form and survive in space, under conditions unlike any other molecular cloud in the galaxy. The temperature, the radiation environment, the turbulence, the magnetic fields, all different from the typical molecular cloud. The molecules found inside the zone reveal how chemistry adapts to extreme conditions, which has implications for understanding chemistry across the universe, including the chemistry that preceded the origin of life on Earth. Stellar evolution at the galactic center, particularly the mystery of how young stars formed in a region where formation should be impossible, tests models of star formation in conditions that no nearby star-forming region replicates. Whatever mechanism allows massive stars to exist so close to a supermassive black hole is a process that must also operate in other galaxies with dense cores. The galactic center does not just raise questions about one location. Each answer or each confirmed mystery at the center illuminates processes happening at scales from individual particles to the structure of the entire universe. And right now, there is a great deal we still cannot see. The galactic center is 25,800 light-years away. Between Earth and the core lies a nearly continuous curtain of gas and dust. This curtain absorbs visible light almost completely. If you point an optical telescope at the galactic center, you see the dust. You do not see through it. This is not a minor observational inconvenience. The dust absorbs roughly 1 trillion times more visible light than the galactic center can send through, a factor of 1 trillion in absorption. Visible light astronomy of the galactic center is essentially impossible from Earth's surface. Radio waves and some wavelengths of infrared and X-rays pass through the dust. That is how almost everything confirmed about the galactic center has been learned. The stellar orbits were tracked in infrared. The radio signal of Sagittarius A star was discovered at radio wavelengths. The Fermi telescope observed gamma rays that also pass through the dust. But the dust absorption is wavelength dependent. It blocks some infrared wavelengths more than others. X-rays above a certain energy pass through, those below it are absorbed. This means the view of the galactic center is patchwork. Certain phenomena can be observed. Others remain hidden because they emit primarily at wavelengths the dust blocks. What cannot currently be seen includes the innermost dynamics of Sagittarius A star's immediate environment at the scale needed to test detailed accretion models. The Event Horizon Telescope image revealed the shadow, but not the fine structure, of the infalling material at the smallest scales. Higher resolution radio imaging could reveal this, and planned upgrades to the Event Horizon Telescope network aim to achieve it. Individual pulsars inside the central molecular zone remain unresolved at the galactic center's distance. The galactic center excess debate cannot be settled until telescopes resolve individual gamma-ray point sources in that region. This requires either dramatically larger collecting area for gamma-ray telescopes or observations from a detector in space with angular resolution far beyond current instruments. The internal structure of the G objects is completely opaque. The merged binary cores, if they exist, sit behind dust shells thick enough to block even near-infrared telescopes. Longer infrared wavelengths can penetrate deeper into dust, but sacrifice angular resolution in the process. A space-based infrared telescope optimized for long-wavelength high-resolution imaging could potentially see inside the G objects. No such telescope currently exists. The magnetic field structure of the galactic center at small scales remains poorly mapped. Understanding Andy's object and the cosmic ray barrier both depend on knowing the magnetic field geometry in detail. That requires many more polarized radio sources in the galactic center region to perform Faraday rotation mapping at high angular resolution. Several next-generation observatories directly target these gaps. The Cherenkov telescope array, currently being built in Chile and Spain, will provide unprecedented gamma-ray sensitivity in the energy range most relevant to the galactic center excess. The next-generation Event Horizon telescope upgrades will improve angular resolution of the core. The Square Kilometer Array, a massive radio telescope network under construction, will survey the galactic center in radio wavelengths at sensitivity levels dramatically beyond meerkat. The galactic center is not hiding. It is broadcasting in every direction. The instruments to receive all of its signals are simply still being built. Step back from each individual mystery at the galactic center and look at all of them together. A supermassive black hole surrounded by stars that should not be there. 6 objects that survive what should destroy them. An invisible wall that blocks the fastest particles in the universe. A gamma-ray glow with no confirmed source. Random radio signals from an unidentified object. Orbital deviations in stars that the standard model cannot fully explain. An alternative theory suggesting the black hole might not even be what it appears. Every one of those anomalies could have an explanation. Some have strong candidate explanations. None has been definitively solved. The question worth asking is whether this concentration of mysteries in one location is expected or suspicious. In science, anomalies cluster around the places we look hardest. The galactic center is the most intensely observed region of the galaxy outside the solar system. Telescopes have pointed at it in every available wavelength for decades. The sheer volume of data collected from this one region vastly exceeds what is available for almost any comparable region elsewhere in the galaxy. More data means more opportunities to find things that do not fit. This is a real effect, and scientists are aware of it. Some fraction of the galactic center's mystery list is probably the result of observational bias. Look anywhere hard enough and you find anomalies. The galactic center gets looked at harder than almost anywhere else. But some of the anomalies at the galactic center are properties of the environment itself. The extreme conditions, the proximity to a supermassive black hole, the density of stars, the intense magnetic fields, the enormous gas reservoir, genuinely do create physics that does not operate the same way elsewhere. The G objects exist because of the specific gravitational and stellar density environment near the core. The cosmic ray barrier exists because of the energy budget of the galactic center. The gamma ray excess exists because the dark matter density or pulsar density at the core is higher than anywhere else nearby. These are not artifacts of looking hard. These are real physical features of a genuinely extreme environment. The pattern of anomalies reflects something specific about the galactic center. It is a place where multiple physical processes, each operating at or near its extreme limit, intersect. Gravitational physics at 4 million solar masses. Magnetic physics at field strengths 1,000 times the galactic average. Chemical physics in a molecular zone unlike any other. Radiation physics in a region producing gamma rays, X-rays, and radio waves simultaneously from multiple overlapping sources. Each anomaly connects to the others. The cosmic ray barrier shapes the chemistry of the central molecular zone. The magnetic fields affect the G object's survival. The dark matter density underlies both the stellar orbits and possibly the gamma-ray excess. Andy's object reveals the magnetic environment that the cosmic ray barrier requires. The galactic center is not a collection of separate mysteries. It is one deeply complicated system where each piece of the puzzle interacts with every other piece. And the researchers who study it, who spend their careers analyzing individual components of this system, consistently express the same sentiment in different ways. The models are breaking more than they are holding. The word afraid is not one that scientists use lightly. In published papers, the language is careful, cautious, measured. Phrases like unexpected, unaccounted for, inconsistent with standard models. But in conference talks, in interviews, in the conversations that happen after the formal presentations end, the word that surfaces more often than any other about the galactic center is humbling. Humbling is the polite version of afraid. Here is what the researchers who study the galactic center actually know. The standard model of the galactic center, a supermassive black hole surrounded by a dense stellar cluster, embedded in a molecular gas zone, producing well-understood outflows, should be able to explain the basic features of the region with known physics. And it does explain many things. The stellar orbits broadly match. The black hole mass is confirmed. The outflows are real and detectable. But the model fails consistently at the edges. The G objects survive when they should not. The gamma ray, excess, has no confirmed source after 15 years of study. The cosmic ray barrier has no confirmed mechanism. Andy's object fits no known category. The fast-moving stellar orbits carry residuals. The dark matter core alternative remains mathematically viable despite the Event Horizon Telescope image. Each individual failure could be a gap in data, a measurement uncertainty, a missing component that will eventually be found and plugged into the model. Scientists would be comfortable with that interpretation if the failures were isolated. They are not isolated. They cluster, they connect, and they resist resolution despite enormous effort and increasingly powerful instruments. What researchers are cautious about, what keeps some of them genuinely uncertain in a field that is usually good at narrowing down answers, is the possibility that the galactic center is showing them the edges of known physics, the place where the models that work everywhere else begin to break down because the conditions are too extreme for the approximations those models rely on. General relativity works at the scale of orbiting stars near the galactic center, but its behavior at the scale of the event horizon, in the infalling plasma, in the immediate vicinity of the singularity itself, is untested. The quantum behavior of matter under those conditions is not described by any confirmed theory. Quantum gravity, the as-yet undiscovered framework that would merge general relativity with quantum mechanics, is exactly what would be needed to describe physics at the galactic center's most extreme scales. The dark matter problem is another edge. The galactic center is the most likely place in the galaxy to find evidence of dark matter's particle nature. If the galactic center excess is dark matter annihilation and current instruments simply cannot confirm it, the implication is that our detection capabilities are not yet adequate to answer one of the deepest questions in physics. What scientists are afraid of, stated plainly, is that the galactic center is telling them something true about the universe and they do not yet have the language to read it. That is not a failure. That is where science actually lives, on the boundary between what is understood and what is not. The boundary at the galactic center is wider than almost anywhere else in the observable universe. 25,800 light-years away, the center of our galaxy is running experiments that physics has not fully solved. Every telescope pointed at it is listening for the answer, and the signals keep coming, strange, polarized, unexpected, and not yet explained.